So the first transformation is the rotation by just multiplying with the rotation matrix, which is this kind of cryptic looking code, but in reality it's cos negative sin cos matrix with just the angle that we have, and we can rotate our original vector by any degree that we want. We're not going to make it longer, we're not going to make it shorter, we're not going to change anything about it, just rotate it by the angle that we want. We can even plug in another number like 45. Let's run this first. So we can imagine this matrix in particular as a rotation matrix, and this is what it's called exactly. With any radian degree we want, we can just rotate our vector and transform it to any degree or angle that we want. The next transformation is a scaling transformation. So what this matrix does is that it makes our vector go twice as long in the x coordinate and 3 times as long in the y coordinate. We can again play around and try, for example, 2, 1 to make it shorter here, 2, 0, 5, even shorter, or as basic as 2 to only making it go twice as long for the x coordinate and y coordinate. The next example is the shear transformation. And this is the x shear, the x direction shear. What it does is that it makes the vector go further in the x coordinate. The opposite is the y direction, the y direction shear. And what it does is that it makes the vector go higher up on the y coordinate. Another example is reflection. It creates a symmetrical vector along the x-axis. Please feel free to play around with the numbers. You can make any transformation that you want just with those. We can create anything basically just from the 1, 1 vector. And finally, the reflection across, or no, there's one last example after this. The reflection across the y-axis, just like the x-axis, just across the y. And finally, the reflection across the y equals x, this axis, the one going in the middle. And those are the basic transformations that can basically turn any vector and move it to any other position that we want. We can go further in the presentation before we finish on the next examples. So, in machine learning, it's pretty important to know what these transformations can lead to. And since manipulating a vector is not always necessarily just to rotate it or to shear it or to scale it, it's generally stacking multiple transformations at once. And this concept is basically used all the time in deep learning, for example, where our data isn't only passed through one iteration of transformation, it's moving through many layers in the network, and the data is being transformed in each layer. So, for example, one important thing to know is that if we multiply b by x and then multiply by matrix A, of course the x is the vector that we want, is the same as multiplying A by B and then by x. Why? The demonstration here is just applying basic, this is the formula that we've seen in the past. We can arrive very easily at the same result. But we have to avoid thinking like this. Multiplying A by B is not the same as multiplying B by A. Again, demonstrated by just applying the same formula that we've seen, multiplying a matrix by a vector. Again, keeping it simple, just a 2 by 2 matrix. The results are different, and we can even see it here in the code. Wait. I don't know if I'm not getting questions because it's very clear and easy, or because you guys are shy. Feel free to ask at any second to raise a hand and ask a question. So uh, here we have applied two transformations: a scaling transformation and a rotation transformation. In the blue vector and green vectors are the transformed ones. The blue one was the red scaled then rotated. The green was the red rotated then scaled. Obviously, it's very different. We get a completely different result, a very new vector. It's not the same, and same goes if we like to imagine it in deep learning context, for example. Um, we cannot really switch the layer order, of course, and here I wrote it, order matters. And something else that I would like you all to imagine with me is that vectors are not really always this red line, blue line, green line. It's not always an arrow pointing somewhere. We just visualize the vector by a point to where it stops, to where the arrow points to. And that's enough to visualize a vector, right? We can know where the arrow is. And if we're going to visualize all the points in space as vectors, we can draw shapes with vectors, right? For example, a circle is just a circle of points, right? So in this example here, we have tried scaling and rotating a square-shaped set of points, or just a square, since it's just a set of points. If we apply scaling and then rotating it, it's this rectangle over here. Well, if we rotate then scale it, it's a completely different shape. So yeah, this is a very common imagination mistake that we have to avoid. And how this translates to machine learning, let's imagine just this simple network of input layer and an output layer, nothing going in between. Each output layer would have his weights, or its weights, the blue one with W1, W2, W3, W4 for each node, and so on. And these observations, I know they're called X1, 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 but it's actually X1 for observation 1, X1 for observation 2, and so on. And then there's our biases. Each neuron would have its own bias, blue and green and orange. After applying, well, I know this does look like matrix to matrix and then vector addition, but in reality, we can imagine if we had just one observation, right? If we only had one observation, we would have one set of weights here, and again, three, what's it called? Oh, I'm sorry, no. This full matrix, I apologize. This full matrix of weights, but we only have one observation, which is our vector, matrix to vector operation. And then this operation's output is a vector, of course, as we've seen. An add in a vector would give us an A1, A2, A3, another vector, which is the output of this neural network. So yes, this is the whole concept of deep learning. This is what neural networks are doing. It's just a lot of matrix to vector multiplication, output in a vector and feeding it to the next layer, and so on. Another application of matrix transformations is in data augmentation. So if we had an original F letter in an image, multiplied by identity matrix, which basically does nothing, it's this. We can apply any linear algebra function to an image with, like, the image is just a matrix, right? It's a matrix of pixels. and each pixel is just a number, a scalar that we can use. We could stretch it like we've seen in the examples. We could use the reflection, stretching and reflection, and so on, shearing, rotating, and whatever. And this does generate a lot of new data to train our models, especially in image data. When training, maybe for letters in particular, we would not use rotations and what's it called, reflections, because maybe the letter changes and so on. But for example, in detecting faces and whatever, it doesn't matter the orientation. We want to predict the same person. So it does really help in training models. After learning about these basic transformations, we have to learn about determinants and traces. Determinants, for a formal definition, what they are is that they serve to express the volume scaling in higher dimensions. This might sound confusing, but what it does, it really just, the determinant is just a number to summarize the transformation that we have. Since each matrix to us now is a transformation for vectors, right? We want to know by how much. How much is this matrix going to transform our vectors? Let's go on with the reading. So if the determinant of a matrix is 1, that means that it does not change the volume or area of a transformed shape or of transformed shapes. And if the determinant is 0, that means that it collapses a dimension or more. We can imagine this easily in 3D and 2 dimension. For example, if we had a cube and we, as a shape, that's normal, right? And if we're multiplying it by a matrix whose determinant is 0, that means that this cube is going to collapse on itself. One side, or any 2 parallel sides, are going to collapse on each other, and the volume becomes 0. And thus, our cube will transform into a new 2D object, right? The same going for 2D objects. For example, a rectangle would have any 2 sides collapsing on each other, transforming into a line. And this is if the determinant is 0, of course. And if it's 1, that means that it does not change the area. If it's more than 1, that means it's going to make the shapes bigger, and the opposite if the values between 0 and 1, making the shapes smaller. But how do we calculate the determinant? Let's start with the easy base case, the 2 by 2 matrix determinant. And we've all seen this in class, in any linear algebra. The determinant of this little matrix, this 2 by 2, is AD negative BC minus CB or BC. And apologize. So that serves, sorry, I'm just reading questions. That serves to PCA the collapsing thing. Well, we do use the determinant in many crucial steps for PCA, but the PCA's role isn't really to check if the dimensions collapse on themselves. We're trying to remove dimensions in PCA, and we'll see a very gentle introduction. Hopefully, we'll get into it in a future presentation, future session. But no, it doesn't directly contribute to that. And for this part, this equation maybe looks confusing to some of us, but it's really not confusing at all. I'll just draw a small 3 by 3 matrix to extend this formula of 2 by 2. And this formula can go indefinitely. For any matrix size, we will apply the same thing. So for this matrix, let's just use small numbers: 2, 1, 4, 7, 3, 8, 4, 1. Okay. The determinant of this matrix is equal to, we can go through the, across the x or the y. It's the same. I'll do both, it's okay. So we can start with the 3 here. Try not to 3 times what? Times the determinant, like we've said here, for each j going from 1 through n. We multiply it by -1 to the power of I plus j. And since we're at the first column, first row, I plus j is 2, and -1 to the power of 2 is 1. So it's not -3, it's plus 3. I'm trying to keep it clean so we can read it later. So 3 times what? Times the determinant of mij. What's mij? Is the remainder of this matrix if we remove the row and the column of this 3. So we now have to compute the determinant of 7, 3, 4, 1. If we remove this row, this column, this is what we have left, right? And computing a 2 by 2 matrix is by applying this formula. We have reached the base case. But it goes on. It's the sum of this coefficient. So it's negative now, 2. And let's remove this column and this row. We have this 4, 3, 3, 1 remaining. 2 times the determinant of 4, 3, 3, 1. And finally plus, well here the I plus j equals 3. Because it's row 1, column 2. So we do get the -1. And here again it's 3 plus 1, so it's a positive sign. 1, that's right, it's okay. Determinant of 4, 7, 3, 4. And this expression here gives us the information that we have talked about in the past, which is the determinant of the 3 by 3 matrix. I'll go really quick with expanding through the y-axis. It's the exact same, 3, 4, 3. I'm sorry. Removing this and this, leaving us with the 2, 1, 4, 1. And these two are equal, of course. They are both the determinant of this big matrix, or this 3 by 3 matrix. So yeah, going back here, I don't want you to be scared of many letters going here. It's not complicated at all. And the same does extend to bigger matrices. As long as it's a square matrix, of course. It has to be n by n square matrix. We can apply the same, always removing one row, one column, making each matrix smaller and smaller until we reach a 2 by 2 matrix that we can calculate like this. So now about the trace. The trace is a lot more simpler. It's simply just the sum of diagonal elements. Just to visualize it, it's this diagonal. So the trace, is equal to 11. Is my, okay. So where do we need these exactly? And answering Ala's question, what's a lot more interesting about trace, since it seems very trivial here. The trace is the sum of all eigenvalues that we're going to discover, don't worry. And let's also note that the determinant is the product of all eigenvalues. It's very interesting here. So now let's discover what eigenvalues and eigenvectors are. Go into our next section. An eigenvector of a matrix, noting that each matrix has one eigenvector or more eigenvectors, depending on the dimension of a matrix, or linear transformation, since we can call our matrix a linear transformation at this point. An eigenvector is a vector that only gets scaled, stretched, or compressed when the transformation is applied to it, but not rotated. So when a vector is transformed using a matrix, and if it does not get rotated at all, that vector is called an eigenvector of that matrix. That means that it stays in the same direction. It's okay if it gets longer, shorter, or inverted, but it stays in the same direction, and that's what makes it an eigenvector. So formally, if A is a matrix and V is an eigenvector, then A times V is equal to lambda times V, lambda being a scalar. So lambda is the eigenvalue corresponding to that eigenvector in particular, and it tells us by how much the eigenvector is scaled. And the eigenvalue, more formally, what it expresses is it's a factor by which the eigenvector is stretched or compressed during the transformation. If lambda is greater than 1, then the vector is stretched. If lambda is less than 1, then the vector is compressed. If it's equal to 1, the vector stays the same. Since we said it's not rotated, and if it's equal to 1, then it means that it doesn't get stretched or compressed. It stays the exact same, not rotated, not scaled. If it's equal to 0, then it means that this vector in particular becomes 0 when multiplied by this matrix. So now let's move to how to find the eigenvalue. Eigenvalues can be found by solving the characteristic equation, determinant of A minus lambda I being the identity matrix that has all zeros except in the diagonal. It's all ones. By solving the determinant of A minus lambda identity equals 0. So for example, this 2 by 2 matrix, just any example, A, B, C, D, we compute A negative lambda, B, C minus lambda equals 0. We have to solve for this determinant. We'll go through the steps here. As we learn to calculate the determinant, it's this multiplied by this, negative this multiplied by this, of course. So this equation here equals to 0. We can just do the multiplication, expand it, lambda squared plus a factor times lambda plus a constant. That's a basic, what's it called? A basic second degree polynomial. We can just solve it using the quadratic equation. And we get two eigenvectors here, which are the plus and minus. So we'll not really get very deep into the maths or proving it, but the calculation of eigenvectors and eigenvalues is, as always, not very complicated. Just solving a second degree polynomial. That's it. So after finding the eigenvalues, the eigenvectors can be computed by solving A minus lambda I times V. And for each lambda that we have found here, we have a different vector solution, of course, where lambda is the corresponding eigenvalue, so we can find its eigenvector. For each eigenvalue, we substitute it into the equation for any lambda we have, multiplying it by the vector and solving for 0. So we get this system of linear equations, and we simply just solve the system. And so for y gives us the eigenvectors for a particular eigenvalue, and then we do the same for the second eigenvalue, for example. And we get the eigenvalues for eigenvectors for that matrix. And now looking at Google's PageRank, this is a very interesting application of eigenvalues. Says here connection lost. My live okay? Any Okay, all good.
So
Let's not dive very deep into Google's PageRank, but what this algorithm does is that it can calculate how likely is a site to be visited, and this algorithm is very reliant on calculating eigenvectors for matrices. Uh, I wish we had more time to get deep into this. It's very interesting, very fun. But I only want to show you the importance of calculating eigenvectors, even not in machine learning contexts. It's very useful for calculating any type of flowing data. For example, here are other applications for eigenvalues and eigenvectors. Uh, for example, detecting communities in social networks, kernel-based machine learning, support vector machines, diagnosing artificial neural network gradient problems vanishing gradient and exploding gradients. They can be diagnosed and found. We can find these problems using eigenvector calculations. It's used for signal processing, NLP, face encoding, image compression, and SVD that we are going to use for PCA that Ella asked about. And let's move to what SVD is, singular value decomposition. All right. So SVD, it's a matrix factorization technique, and let me tell you why factorization. Because it makes it seem like we're doing something complicated here, but it's very interesting. How can I hide everything? It's okay. I'll just write the factor start here. It's easy. X 3 x plus 2. This is a factorization of a polynomial. This polynomial exactly x squared minus 3x plus 2x or negative x minus 6. This polynomial here, which is x squared minus x minus 6, in mathematics, in class, it's kind of hard to manipulate this polynomial. It's hard to just eyeball the roots, the solutions for 0. It's hard to move on with it. And it makes it a lot easier to factorize it. Turn it into this equation here is a lot more easy. We can just extract instantly this equals 0 or this equals 0, and we can instantly arrive to solutions. While here we have to move through quadratic equation and so on. For a computer, it's also a lot more simple to see an equation like this, to see a polynomial like this. And factorization for a matrix is almost the same as factorization for polynomials. So SVD is a technique to factorize a matrix and it generalizes eigenvalues or eigenvalue decomposition for all matrices, even non-square ones. As we've said in the past, determinants and eigenvalues can only be calculated for square matrix, an n by n matrix. While an SVD helps us factorize any n by m matrix. Factorize any n by m matrix into matrices that are m by m and n by n, that we can apply what tools we have. We can apply our tools on. So A equals U sum V T. U being the left singular vectors. We'll get into it in just a second. Which is an orthogonal matrix. Some here singular values matrix, which is a diagonal matrix, and then the right singular vectors. And here's how it looks like. For any n by m matrix, we can turn it into an m by m matrix, an n by n matrix, and the singular vectors matrix. The singular values are the square roots of eigenvalues of A transpose multiplied by A. This Well, a transpose of a matrix, in case we haven't seen it, I really remember from first session. A transpose of a matrix is just a matrix rotated 90 degrees. Well, not exactly. It's kind of symmetrical to the matrix that we have. It's the same matrix, but we're going to write columns horizontally. Let me visualize by an example. I think that's better. So this matrix, make it bigger. Transpose equal to 3, 1, 2. This column has a row, and the same goes for the others. 7, 3, 1, 4, 3, 7. After that, we multiply this matrix by the original matrix, AT times A. Of course, this doesn't equal A times AT. And that matrix is the singular value matrix. This one in the middle. The right one is the eigenvectors of A transpose times A. And the left one is the eigenvectors of A times A transpose. I'm sorry. And maybe I should. Okay. Before going into applications, apologize. We can get back to the code. There's a small code here. For all that we've learned, there's a TensorFlow function that just does everything. We just use TF dot linear algebra dot trace of A for any given square matrix. And again, same linear algebra determinant of A. You can just print later. It does all the math for us. And we can also calculate the eigenvectors and the eigenvalues of a matrix as simple as TensorFlow.linearalgebra.I of A. And we get the eigenvalues of A and the eigenvectors of A. And I want to show you something very interesting about the eigenvalues and how much information they preserve. Because we're going to see here, sorry for a small spoiler, is that it serves mainly in data compression, noise reduction. Again, in the code, we've defined a 3 by 3 simple matrix. We have computed the SPD, getting the SUV parts of the matrix by again using just TF.linearalgebra.SPD. Everything exists in the linear algebra component. And what it does output is those three values here: 16.84, 1.06, 2.87. These are the this is times 10 over 10 to the 7th. So these are the eigenvalues of this matrix. And those are the singular values of this matrix. And this singular values matrix is a diagonal matrix. So these three values go like this. 16.8 4 1.06 2.87 10 7. This is what a diagonal matrix is. Only the elements in diagonal have values different than 0. So we can just construct it from this vector. And then we have the left singular vectors, the right singular vectors, all calculated through TensorFlow linear algebra component. And after calculating the SVD, we can just apply this formula here. U times diagonal of S times V transpose gives us basically the same matrix. Try to zoom. This is as close as it gets. We have to excuse the floating point inaccuracies for just 3.99969. It's very close. It's basically conserved information about the original matrix. And we can imagine our matrix to be any image, any data set of any type of information about I don't know, about the business and so on. So getting the singular value decomposition of a matrix basically converts it into an n by n matrix, an m by m matrix, and a diagonal matrix that basically have all the information about the original matrix. And them being square matrices allows us to apply all the operations we have. We can get the determinants, we can get the eigenvalues, and so on. So what else can we use SVD on? It's used for image compression, for example. It serves for denoising images, making them clear. We can use it in PCA, which we will hopefully see in the next session. It will be all about PCA and more about singular value decomposition. Since PCA relies heavily on SVD, reducing data dimensions while keeping key features, we can solve ill-conditioned systems, providing stable solutions for nearly singular systems. And it's used for recommender systems, for collaborative filtering, like Netflix and Spotify, help in recommend products for customers. And nearing the end of the presentation here, these are the sources that I used. Again, our favorite machine learning mathematics book, mmlbook.com, and 3 Blue 1 Brown YouTube channel. Thank that guy a lot. And for the Q&A, I really hope to get questions, and I'll try to explain everything that I can. You mentioned some real examples that use eigenvectors like PageRank or community detection. If you could send some sources to read a bit more about that later, that would be great. I mean, in the Wikipedia page of PageRank, you can discover how the algorithm works and where everything is used. For community detections, again, they are famous algorithms that are known, that depend on matrices as information, and eigenvectors serve to answer questions. So yeah, looking at implementations, where you want to look is proofs and implementations of these algorithms. And I will look later to maybe share other links in the community group. Guys, any question is welcome. Don't feel shy for asking. Was there a slide that was not clear or anything I could go over again? No, thank you. I hope everything's clear. Sometimes when everyone is silent, it's scary. Oh, great. يعطيكم انتم الصحة. شكرا لحضرتكم الكل. We're sorry again على الوقت اللي اخذناه في الأول.
حاولت نفسر فيه ساعة سيمفوني زربت شوية باش ما نفتوش ثمانية ونص يا أخي مش نفتح 48. أما إذا كان الناس الكل فهموا خلطنا البوينت اللي حاجتنا به. يعطيكم الصحة نسكت. Okay. Just close the meeting. Thank you again. Have a great night.